Hey, welcome back. Today we're gonna continue on with our trigonometric ratios. This video is mainly focused on objective 1. Use the sine, cosine, and tangent ratios to determine side lengths in right triangles. With respect to WRT is with respect to special right triangles, the items we have been talking about. In this video, we're actually not going to get to any of the key examples. We are going to talk about SOHCAHTOA again very quickly, and we're going to go through a few pieces of it. So, in order to find side lengths of a particular right triangle, the relationships that we use are called trigonometric ratios. They are the sine, cosine, and tangent. And in each case, they represent a ratio of two sides of a triangle. The sine, for example, is the relationship of, well, with the particular angle, it has the relationship of the opposite side to the hypotenuse, okay? The cosine with respect to a particular angle has the relationship of adjacent to hypotenuse. And the tangent of an angle has the relationship opposite to adjacent. And where are we getting those from? We're getting them literally from SOHCAHTOA, okay? If we can remember SOHCAHTOA, we're pretty good, okay? That will tell us the relationships that we need to know. Sine is the opposite over the hypotenuse. Cosine is the adjacent over hypotenuse. And the tangent is the opposite over adjacent. So these three representations in two different ways should help give you an idea of how to look for the actual side in particular that we're looking for, or the sine, cosine, or tangent of a particular angle. And we'll show you that momentarily. The next thing I'd like to do is just show you a geometric viewpoint. And here we have a regular right triangle labeled with its hypotenuse and two different legs. And what you'll notice here is I said let alpha be an angle and let beta be an angle, okay? So those are just the two angles, alpha and beta, that we are talking about. So, what do we really need to understand? We need to understand the opposite side to a particular angle. As we recall, we remember a long time ago that the angle really makes the opposite side. So if I look at this triangle here and I look at alpha, I look opposite of that angle, and I've labeled it OP with a subscript alpha. That indicates that that red side is the opposite side to alpha. In the hypotenuse will always be opposite of the the right angle will always be opposite of the hypotenuse. The hypotenuse and the right angle are always opposites to each other because the 90 degree will make the largest side. The adjacent side just means next to, and that is also labeled in red. You'll note that I've also done the same with the blue, beta. I look opposite to beta, I label it OP sub beta. I look at the hypotenuse, I label that. And then I look at the adjacent side, and we label that appropriately. Okay? So, The image that you always want to have is this nice right triangle and the three angles that you're going to be looking at, okay? Now, there are going to be some variations here, of course, but we're going to look at them a little more in detail. So here are some basic concepts of what we're actually talking about and how we're coming to form these ratios that we're going to talk about, the sine, cosine, and tangent. So the concepts. What first thing that you want to do is find the angle in question. In our case, alpha or beta. The second thing you want to do is locate the side that is opposite that angle in question. The third thing you want to do is label that side that's opposite the angle. So you want to be able to identify the angle and its opposite side. Step 4, if you will locate the right angle. You're going to label the side that's opposite the right angle as the hypotenuse. And finally, you're going to label the adjacent side. If you follow this basic set of rules, you will never mislabel your triangle. And mislabeling your triangle is where many people will make some errors. So be very careful about that. Okay, so what are the three trig ratios for both angles, alpha and beta? So what you can see here is I've listed a whole bunch of stuff, right? I redrew the triangle in question with both angles, alpha and beta, and then I decided to label all of the trig functions that we have. Now, I've left a few things blank for a reason. But if we look at number 1, so I'll highlight what I'm talking about now. I'm talking about number 1, the sine of alpha. So that, remember, is the opposite side because so, ka, toa. So, sine is opposite over hypotenuse. So, the sine of alpha is the opposite of alpha over the hypotenuse. You can keep going on through and being able to identify based on those basic 7 steps. Let's look at number 4, actually. And I'm going to use the darker blue here because that's what I was using up there. So what should I put in here? Yeah, that's right, beta. So in all of these, this is a specific ratio of the two sides of the triangle related to the angle in question. Okay? All right. Now, we have all this information, all of this together. Let's start looking at a very special one. Okay? Our 45, 45, 90. And we spent just a little bit of time on it. We now know how to work the system a little bit here. And what I'm going to tell you is that I'm purposefully assuming that the hypotenuse is equal to 1. At the time, right now, I'm not going to tell you why explicitly, but 1 is a really nice number to work with. You can multiply it by any number and you get that number in return, like 1 times 5 is 5. So there's some very valuable pieces to making that hypotenuse 1. So in purple here it says, what must we find? Well, the obvious thing is we must find the missing sides of our 45, 45, 90. It's a special right triangle. And in the red box that we have down over here, I reminded you about the essence of our triangle. The relationship is S root 2. So we know the hypotenuse is 1, and we know the hypotenuse of this special right triangle is S root 2. So what we are going to do is we are going to set those two things equal to each other. We're going to set the S square root of 2, which is the hypotenuse for our special right triangle, equal to the value located within the example of our special right triangle, which happens to be 1. So, and then we're going to solve for s. So as you can see, I just rewrote the original. I then decided to what? Divide both sides by the square root of 2. We then had to rationalize the denominator because we don't want to divide by something forever and ever. That would take forever, and a computer would never be able to do its calculations. It just isn't feasible. So then what we do is we rationalize. We look at the denominator. In this case, at your level, we're saying the square root of 2. So the principal square root of 2 times the principal square root of 2 is going to give you 2, because the square root of 2 times the square root of 2 is the square root of 4. And the square root of 4, in its positive only state, is 2. So you're going to multiply both top and bottom, numerator and denominator, by the square root of 2. Why? Because that's just 1. Right? I'm not changing anything. I'm just multiplying by 1. When you multiply the fractions, you multiply straight across, and you get s to be equal to the square root of 2 over 2. So now we can take this triangle here and actually put in the values. It's root 2 over 2, root 2 over 2. Now that we have all that, let's actually find the sine, cosine, and tangent for the 45. So what we did here is we took the triangle, I rewrote it again, that we can see highlighted. I rewrote it, right, with the sides included, all the values included. So this is the triangle we're talking about right now. So, with everything we just learned, we can now figure out the sine of 45. The sine of 45 degrees is what? Well, the sine is the opposite over the what? Hypotenuse. So, I look at one of the 45s. I'll pick this one. I look opposite it. I see the square root of 2 over 2. So I place it in the numerator. I then look where? At the hypotenuse. And I notice it's 1. So I put the 1 in the denominator, just as the ratios tell us to do. So, once we reduce or simplify this, we can see that any number divided by 1 is just that number. So the sine of 45 degrees is exactly root 2 over root 2 over 2. Okay? Same with the cosine, because remember, it doesn't matter. You could take either one and you're going to be able to get them back. The cosine is the adjacent side. So if I actually just did this, here's the adjacent side, right? All over the hypotenuse. And that's exactly what I did here. Okay? So I did the simplifications, and I'll just box them so we can find them easy. Okay. And the tangent of 45 is 1, easy, because anything divided by itself is 1, right? Junk over junk is 1. So now that we have all of that information, tons of information and concepts, looking over the basic ideas for the trig ratios, understanding the basics of SOHCAHTOA, we can now look at the 30, 60, 90 with their special. And we're going to assume again that the hypotenuse is equal to 1 unit in length. Notice that I've already put the appropriate sides labeled. Always opposite 30 is S. Always opposite the hypotenuse is 2S. And always the last is the S root 3. Like I said, if you label them correctly, you will never go wrong. The calculations are not that bad. So, now what we have to do is we must solve, right? We have to solve for S, because if we solve for S, then we know all the sides of the triangle. And that's going to be very helpful. So, we set 1 equal to 2S from our assumptions, and then we simply divide it by 2. So S is equal to a half. Well, that's a really nice number. We have the lengths for all the sides of the triangle. All we had to do was what? Substitute 1/2 back in to the S's. And that's exactly what I did. So if you're a little confused about where this one came from, well, I'll clear that up for you right here. It says that it's S root 3, but S is equal to 1/2. So I'll do the substitution. It's 1/2 times square root of 3. Well, the square root of 3 is really the square root of 3 over 1. So when I multiply those two together, I get root 3 over 2. And that's where that comes from. So we're getting closer to the end. So it says, what are the trigonometric ratios for the 30, 60, 90? Well, the sine of 30 is what? Well, so, katoa, so, OH, opposite over hypotenuse. So the opposite side to 30 is a half. What's the hypotenuse? Yeah, that's right. The hypotenuse is 1. So the sine of 30 is really 1/2. It's just 0.5. That kind of neat at all? I think so. A lot more here yet. Okay. Now let's do the cosine of 30. Well, the cosine of 30 is ka. So ka, C-A-H, adjacent over hypotenuse. So we know the hypotenuse already. That's 1, so I'll put that in right away. And then, what's the adjacent? Well, we already identified its opposite, so, and we have identified the hypotenuse, so this is the what? The adjacent side to 30 degrees. So I'm just going to put in the square root of 3 over 2, and the square root of 3 over 2 over 1 is simply root 3 over 2, right? These are what we call exact solutions. Okay? The tangent. The tangent's a really great one. It does a lot of great things too, but not just the sine and cosine. But the sine of 30. Well, this one's going to get a little rough, okay, just for a second, because that's TOA. Tangent is the opposite over the adjacent. So we're talking about 30 degrees. The opposite side to 30 degrees is 1/2. The adjacent side 230. Well, it can't be the hypotenuse 1. That's got to be this guy right here, root 3 over 2. So let's put that in. Root 3 all divided by 2. So let's do the calculation out, okay? Let's do it out right over here, and then I'm going to delete a little bit of this to make a little more room. So I'm just taking this out for a second, and I'm going to bring it over here, okay? So what we have here is 1/2 divided by the square root of 3 over 2. That tells us that it's 1/2 times 2 over root 3. Notice that we're multiplying and dividing by 2. Those will cancel, so it's 1 over root 3. But then we have to rationalize, so we're going to multiply by root 3. So what does all of this come down to? Whoops, sorry. What does all this come down to? Well, this is equal to the square root of 3 all over what? 3. Right? Because when you multiply 1 times the square root of 3, you get the square root of 3. When you multiply square root of 3 times the square root of 3, you get the square root of 9, which is simply 3. Okay. So now I'm going to delete all this, just so we can make some room for work. Okay. Now, what's the sine of 60 degrees? Well, now we're looking at this angle right here, right? 60. So we want to know the sine of 60. Well, the sine of 60 is the opposite, so that would be root 3 over 2, all divided by its hypotenuse, 1. So the sine of 60 is root 3 all over 2. Okay. What's the cosine of 60? Well, the cosine of 60 is cosine adjacent over hypotenuse. So the adjacent is 1/2, and the hypotenuse is 1. So the cosine of 60 is simply 1/2. Okay? Okay. The tangent of 60. Tangent, tan, toa. Tan is opposite over adjacent. So I look opposite, which is root 3 divided by 2, all divided by the what? The adjacent, 1/2. Okay? So now that we have that relationship down, let's do the workout. Okay? The square root of 3, just so you can see it all out, divided by 2, divided by 1/2 is equal to the square root of 3 over 2 times 2, which is then going to do what? Well, the 2's will cancel out, so this looks like the square root of 3. So this all breaks down to the square root of 3. These are what we call exact solutions. Okay. All right. So a very base summary of what we just covered. We covered SOHCAHTOA and finding specific values for the sine, cosine, tangent for specific right triangles. You now know that specifically, if anybody ever asks you what the sine of 30 degrees is, you can immediately tell them it's a half. By the way, notice the sine of 30 is equal to the cosine of 60, and the cosine of 30 is equal to the sine of 60. That'll help you out with some things. You okay? So, now that we have all of this information, even more information, right? Why did we learn the Pythagorean theorem and the special right triangle ratios in addition to learning about the basic trigonometric ratios so far? Just to find sides, no less. Well, what I have here is the coordinate plane. I've drawn 3 points, A, B, and C, that are coplanar. They are all in the coordinate plane, the Cartesian coordinate plane. In red, I drew a ray, AB, and noted it as such. What I'm going to do now is I'm going to take each one of these and I'm going to make another ray. So I'm going to go from A to C and I'm going to make a nice ray. Okay? And, you know, it's kind of interesting. Now, oh, I should use a different color. Now I'll make a ray here. You'll notice that we have just developed a 45, 45, 90. And I did draw this to scale. Now, why is this important? Well, we learned about certain things already. We learned about the Pythagorean theorem to help us work out specific problems with any right triangle. We know that c squared, the hypotenuse squared, is equal to the sum of the two legs squared. Now that we have this triangle, we also remember our rigid transformations. And if I took this triangle and just brought it back up here, so if I just reflected it about the y-axis, that means I'd be back 1, 2, 3, 4 here. This would be B prime, for example, right? A would stay A prime, and C would be up, well, 1, 2, 3, 4, it looks like right there. So that would be C prime, and you'll notice that if I make another ray here, and I make another ray here, I get another right triangle. Well, I'm not suspecting you might see the pattern yet. However, let me show you real quick, just to give you the reason why. Dun, dun, dun. Dun-a-loop. Ba-dum, 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 ba-dum. Whoa. Wait a second. Oh, let me move it a little bit over more. Right there. Okay. Now you start to see why I picked the length 1. What I'm saying here is this distance here is called a unit vector. That unit vector is exactly 1 unit. All of this is to start talking about circles and cyclic functions so that, well, not cyclic, we shouldn't say cyclic functions, we say cycles, to the point where we can adequately make predictions on certain revolutions of things, objects, like spinning something, for example, very basic. And you'll notice that there's actually infinite number of triangles inside this for the Pythagorean theorem. So, I'm hoping that you start to realize all of the information that we learned this year should not be forgotten. The algebra, the geometry, and the combinations or integrations of that information. Okay? Now, there's a lot here. Okay? So I'm making this available, the notes, online. They will be up while you are watching the video. We will have a conversation at some point. Please hold your questions until a Zoom meeting so we can better address certain problems. As I said in the very beginning, this was never about doing the key problems yet. This was about using the sine, cosine, tangent ratios to determine side lengths in right triangles with respect to special right triangles. So, if you are so willing and inclined to do so, you might be able to actually do these problems out to a certain degree. Some of them, like number 4, you won't be able to do yet. Why? Because it's asking for an angle, and we clearly didn't talk about objective 2. So, it's up to you if you want to try these, but I am going to do some of them in another video. This video was specifically to cover the basics, fundamentals of what? The sine, cosine, and tangent. Finding sides to specific triangles. Okay? Now, when I go over specific examples, you'll see that we can work through them very quickly. What you need to definitely know, the sine of 30. It's a half. You need to know it. No question about it. It's one of the things you definitely need to know. You need to know SOHCAHTOA. You need to be able to label your triangles correctly. You need to be able to understand the ratios and the relationships for the sine, cosine, tangent for all right triangles. And that's what this was all about up here. This tells us everything we need to know about how to find a specific side or a relationship or ratio for the given trigonometric function like sine, cosine, or tangent. This right here is basically your overview, simplified as much as possible. All right. Hope this helped. Thank you very much. Make sure you have a great day.